Welcome to the NPTEL online course on fractal and multifractals. In previous lectures, we have constructed the hyperspace from the given metric space, and we have proved some fundamental properties of the hyperspace, like defining the dilation of a set in the hyperspace, and proved that the dilation is a closed set, and we obtained the results related with the totally bounded sets. Then finally, we ended with the hyperspace is a complete metric space whenever the hyperspace generated by the underlying metric space is completed. It means that if X is a complete metric space, then H of XD is a complete metric space. So, these are all the concepts we discussed in our previous lectures. Now, we have the enough material to present iterated function systems, and thereby we construct the deterministic fractal in a metric space. So, in these lectures, we are going to discuss about the iterated function system theories. So, for that, first let us start with the definition of iterated function system, and will define what is Hutchinson and Bansley mapping in the iterated function system. But this mapping is initiated or introduced by the Hutchinson, and later it is modified and formulated by the Bansley, so that this mapping we can call it the Hutchinson-Bansley mappings. Then we are defining deterministic fractal via this Hutchinson mapping on the hyperspace of the given complete metric space S. It means we are going to obtain deterministic fractal as a fixed point of Hutchinson-Bansley mapping. Then we are going to discuss how to generate the fractals by using the iterated function theory. There are two algorithms we are going to discuss, and we are going to discuss the College theorem for finding the suitable iterated function system for the given set. For this, let us start with the iterated function systems and Hutchinson mapping. So, let us begin with the iterated function system. Let n belongs to any natural number n, and n suffix n denote the subset 1 to n of n. So, n denote the first n natural numbers. Consider a finite family of contraction mapping F1, F2, Fn on X with contraction ratios alpha k, which belongs to the closed interval 0 and open 1 for each k belongs to ni. So, this iterated function system, this system is denoted as like this one. Here X is a any metric space. Then the system X together with this finite number of contraction is called the hyperbolic iterated function system with contraction ratio factor alpha is maximum among all these things. Here IFS simply referred as the finite set of continuous mapping, we can call it the iterated function system, whereas here we imposing the contraction condition, therefore it is called as the hyperbolic iterated function systems. Now, if F is a mapping from H of x to H of x, so now we can assume that X is a complete metric space. Throughout our lectures, we are going to assume that X is a complete metric space, and h of x is associate hyperface of x. Now, we are defining f from h of x to x of s by f of a is taking all the image of all the point in the set A, where we are taking A is a non-empty compact set of h of x. Since what is h of x? H of x is collection of all non-empty compact subset of x, and if you are taking one element A from h of x, obviously this set is non-empty and compact. So, if f is contraction on x, a mapping f is contraction on x with contraction ratio or contraction factor alpha, then f is contraction on h of x with same contraction ratio. Now, f is a contraction on x. Now, we are going to prove that f is contraction on h of x. For proving the contraction ratio, we need to take two elements in h of x and we need to find the distance between d of a and b. So, this is the Hausdorff metric space. So, we are going to use the Hausdorff metric hd of a comma b to obtain the distance between a and b, and we are going to find again f of a and f of b, the image of a and the image of b under the mapping f, and we need to find the distance between f of a and f of b. If the distance between f of a and f of b is lesser than the alpha times hd of a and b, then we can call it as f of e is a contraction. So, for that, let us take two element in h of x. By the definition of distance between a point and a compact set B, we get, that means we need to take a point here, the point is fixed number, and we need to check the distance between A and every element in B, and finally we need to take the minimum. So, this equation means that we need to fix the number A and find the distance between A and B for all the member of B. So, among all this collection we need to take the minimum, then we will get the distance between A and B. Then we need to find the distance between f of A and f of B. So, in the previous lectures we have used the infimum and supremums, whereas here we are using the minimum and maximum. Since we are taking A and B are compact sets, compact set means it is a bounded set, it always attain it bounds, that means it has the minimum element and maximum element. Therefore, instead of infimum and supremum, we can use the maximum and minimum. So, one can find the distance between f of A and f of B, where this D is a metric in x of D. So, x comma D is the complete metric space, and h of x and h of D is the hyperspace generated by the metric space x, and h of D is the metric which is generated from the metric given in x. So, the distance between f of A and f of B is defined as, we need to take the minimum of distance between f of A and f of B for all B belongs to B, already we take the minimum. Then after that we need to take the maximum among all the number of A, then one can get the distance between f of A and f of B. Then, since f is a contraction mapping with contraction ratio alpha, the distance between f of A and f of B is less than or equal to maximum and minimum of alpha times distance between A and B, B belongs to B and A belongs to A. That means the distance between f of A and f of B, since this f is a contraction mapping with the contraction ratio, we assume that with the contraction ratio alpha. Therefore, the distance between any two element f of A and f of B, or f of A and f of B, we can written as alpha times f of A comma B, sorry, f of alpha times d of A comma B, alpha time distance between A and B. Now, just you can replace here, then the alpha is does not depending on any number here, so we can take it out. Therefore, which is equal to distance between A and B, and we have the alpha. So, distance between f of A and f of B, one can get less than or equal to alpha times distance between A B. So, similarly, one can prove that distance between f of B and f of A is also less than or equal to alpha times distance between B and A. So, already we proved distance between f of A and f of B is less than or equal to alpha times distance between A and B. Now, we obtained this result. So, then now we will find the distance, Hausdorff distance. So, the Hausdorff distance or Hausdorff metric is defined as maximum of distance between f of A and f of B and distance between f of B and f of A. Now, we already obtained this, both the quantity is less than or equal to distance between A B here and distance between B A here. So, again, so it can be written as less than or equal to alpha time maximum of distance between A and B and distance between B and A. So, this quantity is again the Hausdorff distance between A and B. So, it shows that f is contraction on h of x with the same contraction ratio. So, this theorem says that if you define one contraction mapping on x, then f of A you can define as A, where A you can taken from the Hilbert space, f of A equal to set of all f of x such that x belongs to A is again a contraction on h of x with the same contraction ratio alpha. Let us discuss the example for these theorems. Now, we can take x is R is the real number system, and consider the usual matrix distance between two element in the real number system is defined as modulus of x minus 1, and define the mapping f of x equal to 1 by 2x. So, one can verify that this is the contraction mapping in the real number system. So, find the distance between x by 2 minus y by 2. So, one can get 1 by 2 times modulus of x minus y. So, it means that the distance between f of x and f of y is equal to alpha times. So, alpha here it is 1 by 2 distance between x and y. So, the contraction ratio here is alpha is 1 by 2. Let h of R denote the collection of all non-empty compact subsets of R equipped with the Hausdorff metric HD. Now, we can take any set A in the h of R, any compact set in R, that is A is a element or subset in h of R. Maybe we need to take A is a member of h of R. Define f of A as f of A such that A belongs to A, that means 1 A by 2 for all A belongs to A. Now, let us take A particularly as 0, 2 and B as 1, 3. If you are taking any element A belongs to h of R, this is the definition of f. We are defining f of A as this one with respect to this contraction. Now, we need to show that this function is contraction. For that we are illustrating with an example. We already proved that this forms the contraction. Now we can take two elements A and B. Now we need to find under this mapping F what is the image of A. So what is f of A? F of A one can get, we are applying this mapping A by 2 on here. So one can get 0, 1, and f of B one can get 1 by 2. So when you are dividing this one, 1 by 2 and 3 is 1.5, it is 3 by 2. So under this mapping F, now F is the mapping from H of R to H of R. Now under this mapping F, the image of this set is given by here 0, 1 and 1 by 2, 3 by 2. Now let us first find the distance between these two set and distance between these two set in H of R, in H of R. So for finding the distance between A and B, we need to find the HD of A comma B, we need to obtain, and we need to obtain what is HD of F of A and F of B. So here two sets are compact sets in H of R. The H of R, the metric is the Hausdorff matrix. So if you want to find the Hausdorff distance from two compact set in H of R, we may use this formula. So what is this one? If we have the two interval, closed interval AB and CD, find the difference between A and C and difference between B and D, and take the modulus and take the maximum between these two elements, then one can get the Hausdorff distance between this closed interval. Then the A and B is, in our case, the A is 0, 2 and 1, 3. A is 0, 2 and 1, 3. So we need to find the difference between A and C and B and T, and we need to take that 0 minus 1 and 2 minus 3. In both the case we will get 1. So if you are taking the maximum, then distance between these two sets A and B is 1. Now we can find the distance between these two sets. Find the difference between this element and this element and this element and this element, and take the modulus. So it is 0 minus 1 by 2, can get 1 by 2, and 1 minus 1 by 2, sorry 1 minus 3 by 2. So one can get 1 by 2 again. So the maximum between these two number is 1 by 2. Therefore the distance between HD of F of A and F of B is 1 by 2. Now the distance, this is Hausdorff distance. Hausdorff distance between F of A and F of B is 1 by 2, and Hausdorff distance between A and B is 1. Then this satisfying distance between image of two sets is less than or equal to alpha times 1 by 2 times the distance between A and B. There is a typo here, it is not DH, it is the HD. So A and B. So what we did here, we take one function f of x and the R, it is defined as x by 2, it is a contraction factor with the contraction ratio 1 by 2. Then we define the function f of A like here, and we are taking two set. This two set we are taking particular example, you can take any arbitrary set, it will satisfying these things. We are just illustrating with an example. Then if you are finding the image of these two under this mapping, one can get these two numbers. Then find the distance between A and B is 1, and find the distance between f of A and f of A 1 by 2. So one can arrive to this one. So you can conclude that f of A also contraction in H of R with the same contraction factor alpha equal to 1 by 2. So, now let us prove the theorem related with the 4 element in the H of x. The H is any metric space, but particularly we are taking at the complete metric space. If you are taking 4 members in the Hausdorff space H of x, then Hausdorff distance between the union of A and B and C and D is less than the maximum of the Hausdorff distance between A and C and B and D. This we can prove. Let us take 4 element, then we have the Hausdorff distance between A, this side we can prove the Hausdorff distance between union of A and B and C and B can be written as the maximum of the distance between A and B and C and D and distance between C and D and A and B, the symmetric. There are 2 possible cases. So, what are the possible cases? The Hausdorff distance between A union B and C union D equals distance between A union B and C union D. This one case. Second case is the Hausdorff distance between these 2 element is equals this one. Let us discuss the first case. If the Hausdorff distance, because we are choosing the maximum among these 2, if suppose this is equal this number, then a distance between A union B and C union D can be written as distance between A of C union D or A of A union B or C union D, which is equal to distance between B of C union D. There are 2 cases. Suppose distance between A union B and C union D equal to, again the first one, this one, the distance between this is equal to this one, then one can arrive the Hausdorff distance between this one equal to this quantity which is less than or equal to distance between A and C lesser than the Hausdorff distance between A and C, which is less than or equal to maximum of Hausdorff distance between AC and BD. So, this case is over. The Hausdorff distance between A union B, C union D is lesser than the Hausdorff distance between AC and the Hausdorff distance between BD. So, here suppose this one equal to this one, we arrived to the conclusion. Suppose this distance equals this one, the distance between A union B and C union D equal this quantity, then the Hausdorff distance can be written as like this one, then this is less than or equal to B and D, because distance between B and D, if you are removing this union set, then it is obviously larger than this one, then this is lesser than the Hausdorff dimension between B and D, because we are taking the maximum of distance between B and D and D and B. Therefore, if you are taking one element, it is less than or equal to Hausdorff dimension between HD and HD of B and D. So, this is less than or equal to AC and BD. So, we arrived at this one. Now, the next case, suppose the Hausdorff dimension between these 2 union is equal to this number, the same argument A union B and C union D equal this number, then this can be written as, this term can be written as distance between union of C and D and A and B can be written this 2 form. Suppose D is distance between C union D and A union B can be written as either this one or this term. If this one is this term, then from the same argument one can get the max Hausdorff distribution between A union B and C union D equal to this one, and if you are taking the second argument then this one and this one, then one can arrive Hausdorff distance between A union B and C union D is less than the maximum of Hausdorff dimension AC and BD. So, in any case, in both the cases we arrived at the conclusion Hausdorff distance between A union B and C union D is less than the maximum of Hausdorff distance between AC and BD. Then after finding the Hausdorff distance between A union B and C union D, here we are taking only two element union, that means A union B and C union D. Whereas suppose you have the n number of mapping, if you have the n number of sets xn, x1, 1, x2, x3, x3, xn is the member of h of x, or yn is the member of h of x, then Hausdorff distance between union of xn, where n running over 1 to some finite number n, and Hausdorff distance between Hausdorff distance between this union and the union of yn, one can arrive to the similar result with this one by using the induction method. So, this is just for the two cases. Now, we can prove this one by induction proof, we can generalize for the n number of mappings. Now, we are ready to define the Hutchinson-Bansley mapping by taking the union of all the compact sets. Let us discuss this mapping in the next class. Thank you.